Hello, hello, hello. Voice check, microphone looks like it's working. Camera looks like it's working. This is great. All right, fantastic. Well, welcome back, my friends. How's everybody? Have a nice week. I see Greg, Abbas, Tony, Harpreet. Fantastic. So before we get started and the rest of our friends are joining us, do you all have any particular questions you'd like to ask me regarding this past week's homework, what's coming up, quiz questions, test questions, schedule? No one's got any questions?
I got a question.
Yes.
Remember,
what is your question?
A couple of weeks ago, you brought it up something about a PLC system that once we finish the 50 class, we can log in.
Yes, that's I mentioned PLC. PLC stands for Programmable Logic Controller. It's an industrial computer used in many places. We have a class that specializes in teaching that. That's offered in the fall. It's only offered in the fall. It's not offered in the spring. And it's on Tuesday nights from 6 until 10.
Okay.
Great class. All right, so I opened up the floor for any questions since not everybody's on, but you guys are on. So any questions regarding your homework, regarding your circuit builds, anything of the sort? Did everybody get a chance to take a look at this week's Canvas? I gave everybody a preview to it yesterday of the PowerPoint that we have for today. And in addition to that, your deliverables list is completed also in Canvas. So you actually had your deliverables list posted yesterday. So that gives you a full more than a week's time to get things done. The assignment sheet, the line items is a lower number of line items. You do have two areas that will help support you in the theory side and understanding side, separate of the reading, are the WISC online electronics videos, which are really helpful. And then in addition to that, I've also got Khan Academy assignments on for you. So you want to check back in Khan Academy and see those. Everything is listed in Canvas, so you should be able to see all of your tasks that are required of you in Canvas.
I just got here. What was the question?
The question is, are there any questions for me?
Oh, sorry.
Regarding your homework, regarding your labs, regarding your time management, regarding your due dates, regarding your assignments, regarding your test and quiz coming up. Any questions for me?
When is test and quiz again?
Okay, we have a quiz on Thursday and we have a test next Tuesday.
Thank you.
How will the quiz work?
Oh, it's simple. It's pretty much open book, open notes, open to everything. Just try not to use Discord and chat each other the answers. No, it's and the preview for the quiz questions I gave you as slide number 2 on this week's PowerPoint, which was posted in Discord the day before, and then uploaded to Canvas last night. Anybody get a chance to take a look at those test questions? What test questions? Nope, nobody's had a chance to look at them.
Is the quiz in class or is it on our own time?
We will, the quiz on Thursday will be right after the 7 o'clock hour. So it will be during our time. That way I can be available for questions and answers if there happen to be any challenges. But if you've been doing your work steadily, there shouldn't be. If you've been very steadily going through your worksheets and understanding what it is that you need to understand from those worksheets, you should be all right, okay? Has anybody had a chance to check their grades on Canvas? Because that will probably I'll probably make that an assignment. A lot of people don't check their grades until, what? It's a week before final exams and I've got these things missing. No. You should be checking your grades once a week. So you'll see something from me before Thursday regarding a task on Canvas. So I think that that's necessary for us to do. What it is that you'll do is you'll go on Canvas and you'll print out pretty much something that looks like a grade report for yourself. Has your name on it, has your average at the bottom, how many total points possible, how many points you've earned so far. So in the first week we had almost 500 points. Last week we had 400 and change. This week we have 400 and change. So it looks like by the end of this week we should be somewhere around 1,200 points total, and you can check where you stand with respect to that 1,200 points total just by going on to Canvas Gradebook and see, okay, am I, at the 90 percentile? I'm at the 85% percentile. Where am I based on the total number of possible points? The big point items this week are not very challenging, but they are some things for you to do. There's 120 points in Canvas. There's in Khan Academy. There's 120 points in the WSIC electronics videos. So it's already 200. Half the points this week are reading the articles, viewing the videos, and such. The other set of points will be coming from your circuit builds and your analyses and things on paper. So now that I have more of you, as you have been submitting things, have you been reading the comments that I've been sharing with you? When you get an alert from Canvas that you got a score on something, you should take a look at comments that I share with you, because I take time to put in those comments where I think that constructive comments would be helpful to you if you're misunderstanding some aspect of your work. So you really need to read the comments that I put in there so that when comes time of our work together this evening, when I ask you to do a task, it won't be coming as a surprise to you that, yes, we're doing things to this particular standard. Okay, so that being said, let's go ahead and welcome everybody. Let me get to my screen and we'll take a look at, it comes up in the background. All right, can everybody see my PowerPoint on your screens? Give me a thumbs up if you can. Cool, all right, fantastic. Slide number 2. All right, potential questions. Can you answer these on the fly? All right, meaning can you answer these without having to look things up? What is the symbol that we use for current? Could you write that down? Get out a piece of scratch paper and say, let's see if you can do this. Let's use this as a practice test. There's the question. Number 1, write down your answer on a piece of paper right now. Don't shout out the answer. We're going to compare them a little bit. So number 1, symbol for current. And then number 2 is what power of 10 is micro? What power of 10 is micro? Number 3, spell the unit for power. Spell unit for power. So you're going to write that down on a piece of paper. Number 4, R for short. So the resistance for a short, okay? R for a short. What is the resistance for a short in some number of ohms? And then number 5, resistance for an open is how many ohms? And then number 6, Ohm's law. So you want to recite what Ohm's law is for the voltage. Number 7, you want to be able to write out what is Ohm's law for current. Number 8, you should be able to write out what is Ohm's law for resistance. Number 9, now Watt's law has 3 circles. Using the very first circle, what is Watt's law formula for power? Number 10, what is Watt's law for current? Number 11, what is Watt's law for voltage? Number 12, electrons have what type of charge? Number 13, something is needed to free electrons. Something is needed to free electrons. So that's 1 through 13. Number 14, the blank band is the outermost band of electrons. The blank band is the outermost band of electrons. What do you remember? And number 15, blank is when we have a complete current path. Blank is when we have a complete current path. Number 16, we can measure resistance. Oh, can we measure resistance when current is flowing in the circuit? Can we measure resistance when current is flowing in the circuit? Number 17, blank is the function name of a DMM for current. Blank is the function name for a digital multimeter for current. Number 18, using only VDF. If you're given VS is equal to 10 volts and R1 is 470 ohms, R2 is 980 ohms, and R3 is 560 ohms, you need to calculate what is the voltage we expect to find across R1, the voltage across R2, the voltage across R3. So R1 is 470 ohms, and R2 is 980 ohms. R3 is 560 ohms, and yeah, looks pretty good. Okay, so we will have VR1, VR2, and VR3. Let's work on those calculations. Number 19, you're given orange, white, gray with red, and red. So you're tasked with determining the coded value, the minimum, and the maximum based on orange, white, gray, red, and red. All right, question number 20. Blank is the specific name for a wire across voltage source terminals. Blank is the specific name for a wire across the voltage source terminals. Number 21. Blank and blank scale are two types of digital multimeters. Number 22. So we have some calculations to make. You have V. So you should have on a piece of binder paper or in your notebook's probably the best place because you're allowed to keep your notebook for using on any future quiz or any future test in any class that we have. So whatever you write in your notebook is gold. It can only be what you write in there. You can't jam papers in there. You can't put Post-its in there. Only what you hand write.
Could you mind repeating that? Your voice kind of got staticky, or it was hard.
Okay, I'll be happy to repeat that. So here we go. So you are allowed to use your notebooks, and the more you enter into your notebook clearly and readily, the more it becomes a ready resource for you to be able to use in any of our ESYS classes. It can only be handwritten. You can't put in Post-its. No Post-its are allowed. No added papers can be stuck in here. Only what you handwrite. So the more detailed, the more clear you're able to make this, the better the resource it will be for your future work.
All right, thank you.
Okay, you're welcome. All right, let's do some of these and see how you did. I will be calling out names. So for question number, sorry, didn't mean to go to this slide. Come back here. All right. Number one, the symbol for current.
Were you asking me, Luis?
Luis.
Yes, the symbol
Mr.
for
Ariza
current is an I.
is a capital I, uppercase I. Everybody in agreement? Very good. Question number two will go to Jess. Jess, what do you have for, whoops, where did I? All right, back on the question set. So question number two, Jess, is what power of 10 is a micro?
That would be 10 to the -6.
10 to -6 would be correct. Excellent. 10 to the -6. Question number three, spell the unit for power. That question would go to Harpreet. Unmute your microphone, Harpreet.
It's a W, capital W.
Read the question, my friend.
This is a P, power.
Read the question.
So watts.
Read the question. Harpreet, are you reading the question?
Yes.
Would you read it out loud for me, please?
Yes. Spell the unit for power.
Spell. Pretend this is a spelling bee. Help me out. Spell.
W-A-T-T.
That's what we're looking for. Thank you. Okay. W is the symbol for watt. If
Okay.
you speak watt, you're not spelling watt. So the instructions didn't ask you to speak watt. The instructions asked you to spell. And spell means you got to give us the letters. Okay.
Okay.
Okay. All right. Just so that we're clear what we're asking for. All right. So question number four, blank is the resistance for a short in some quantity of ohms. Ephraim, what do you have there?
Ground zero.
Yeah, so a short would be 0 ohms. We have 0 ohms on a short. Thank you. Next question is number 5, resistance for an open in some quantity of ohms. Erica, what do you have for that, Erica? If it's open, and I mentioned this last time, you might have missed that. If we're measuring across an open, we're measuring infinite resistance. Okay? That we would use the infinity symbol, infinite resistance. And for some of you who don't remember the symbol for infinity, it looks like the figure 8 sideways. Okay? Thank you. Next one is number 6, Ohm's law. I'm looking for the formula for V. That question would go to Toan.
V equal I times R.
I times R would be correct. Thank you. And the next one is Ohm's law formula for current. Kirsten, what is your Ohm's law formula for current?
V over R?
Would be V over R would be correct. And then number 8, Ohm's law, the formula that we would use for resistance. That question would go to Tony. Tony, what is the formula for resistance using Ohm's law?
R equal V over I.
R is equal to V over I would be correct. Well done. Next, number 12, electrons have blank charge. So Ryan, what is the blank filled in with?
Negative.
Negative would be correct. Negative. Next, number 13, something is needed to free electrons. Anna, do you remember what was that something that was needed to free the electrons?
Energy.
Energy is correct. Energy is what's needed to free the electrons. Okay. Number 14. Number 14. The blank band is the outermost band of electrons. So that question goes to Dana. What do you have there for number 14?
Is it valence?
Valence is correct. Valence, the valence band is the outermost band of electrons. Next one, number 15. Blank is when we have a complete current path. Carlos Navarro, what do we call that when we have a complete current path? A complete path for electricity to flow. What do we call that condition?
I'm not sure, but I'm going to take a shot. A circuit?
Yeah, yes, and there's two kinds of circuits. What type of circuit would you call it? What would be the condition of the circuit if it is complete and allows electricity to flow? It's really close. It does start with the letter C also.
Closed circuit?
Closed circuit, yes, we're getting even closer. It's a circuit and it's got to be closed. And then somebody throw that out there.
Continuity?
The word is continuity, okay? Continuity. Continuity. And continuity was one of the most basic things that you needed to do with your digital multimeter before you could use it. When you go to use your digital multimeter, you turn the thing on and you set it to the LED mode, the diode testing mode. And if you recall, when you put your two probes together and you touch, you will either hear a beep or you will also see, or you will see that the display goes to 000 ohms. And so that means there is continuity between, that means your probes are working, your multimeter is working. So you are doing what's known as a continuity test. So continuity is a really key word and a key concept. It means a complete path for electricity to flow. So closed circuit is the right idea, totally the right idea. All right, next question, number 17, blank is the function name of a digital multimeter for current. Chisamaga, unmute your microphone and share with us what you think the answer for number 17 ought to be.
I put ammeter.
Would be ammeter, A-M-M-E-T-E-R. It is an ammeter. If it's used to measure ohms, what do we call it, class? Ohm meter. And if we use it to measure volts, then it's a voltmeter, okay? Okay. All right, now we have some calculations to do. Number 18, using VDF. Well, it helps if you remember what VDF stood for. We had that as part of our lecture discussion last Tuesday and I think part of the week before. Certainly had it for some additional work for us to do on paper. So VDF stands for voltage divider formula. Voltage divider formula. And what we'll do here is, let's see who has some numbers for me. So let's go and take a look. Greg, do you happen to have the voltage across the first resistor? Did you get to calculate that?
On our circuit builds or right here?
Right here on our practice test.
Oh, no.
Okay. Question goes to Francisco. Do you happen to have that calculation for VR1?
Sorry, I was having a bit of difficulty with that question.
Okay, all right. Well, that's why it's here for us to review, because I don't want it to be difficult for anybody. Luis, do you happen to have a value for VR1?
Yes, I got
What did you calculate?
2.34 volts for the first.
2.34 volts would be correct. And I'm looking for VR2. Jess, were you able to calculate voltage for number 2?
Yeah, I got 4.88 kilovolts.
4.88 volts is correct for VR2. Thank you.
Wait, is it 4.88 volts or 4.88 kilovolts?
It should be 4.88 volts because you're only starting with 10. So that's a really, really good question, Justin. I'm so glad you asked, because if you look at the question, the voltage source, what we're beginning with is 10. So there should be no way we would be able to calculate anything close to kilovolts, because first of all, kilovolts would be lethal. Second of all, we didn't start with that high a number. So even if your calculator spit out some kind of an exponent 3 at the end, you should look at that twice and say, okay, maybe it should not be kilo. I better not write down kilo. Let's recalculate this and see if we're doing this right. Okay, so to answer your question, no, it's whole volts. It should be 4.88 volts. Okay. Okay. The VR3 I'm looking for. Harpreet, do you have voltage across number 3?
I don't.
Okay. Ephraim, do you have the voltage across R3?
Sorry, I'm driving, so I can't.
Okay, no worries. Keep on driving safely. Thank you. Erica, do you have the voltage for VR3?
I got 2.79 volts.
2.79 volts is correct. Well done. Good job. Thank you. And so that takes care of the voltage calculations. Then we're going to do resistances in just a moment. So before we move on, let's just take a pause here and have you understand what some of your classmates just did and what I need all of you to feel comfortable in doing. So let's see if I can get unshare this for a moment. And let's go to camera. Let's see, is it plugged in? It is plugged in, cool. And IPV 4K, cool. And let's go here. So everybody mute your microphones. Let's see if this guy is in focus. Cool, now that's in focus. All right, so the task at hand is called VDF. And VDF stands for voltage divider formula. And the general form of the formula is this: V, voltage for some unknown resistor, we call that VRX. And this is for series circuits. I'm going to abbreviate the word circuits for a moment. This is for series circuits. So voltage across a particular resistor is going to be equal to that resistor over the total resistance times your voltage source. Now that's the general form of the formula for voltage divider. So here, this particular exercise, number 18, says you happen to have a 10 volt voltage source. So here is 10 volts. Here's a voltage source. Here is a resistor. Here is another resistor. And here is another resistor. So you have R1, you have R2, and you have R3. And these happen to be given as 470 ohms, given as 980 ohms, given as 560 ohms. So if we want the voltage across the first resistor, then we write out our formula this way: VR1. So we're no longer the X. The X was unknown. It could be any of those, 1, 2, or 3. But if we want the voltage across R1, then we write it out VR1. And we write out R1 in the numerator position, R total in the denominator position, times VS. So my recommendation to you all is always write out the formula you're going to use. That being said, now we can start plugging in values, because the value of R1 happens to be 470, and the total, we need to total this up, and if you total this up, it should be 2010. Let's go ahead and double check that. Let's go turn on our magic calculator. 470 plus 980 plus 560. Does it take you long to add these guys up? And is it in fact 2010, or in this case 2.01 kilo? Okay, works out to be a decimal 2010, and we're going to multiply this by 10. So keeping things simple, because you don't have to write any of this in engineering notation while you're doing the math. I think if you keep things in decimals, it's a lot easier to work through, and the only time you worry about engineering notation is stating the answer at the end. So do we in fact have 470 ohms for R1? Does the total in fact add up to 2010? And if you look at this, can we simplify keying this into our calculator? In other words, are we really going to key in 470 divided by 2010 times 10? No. Could we whack off a 0 because they appear in the numerator and the denominator? Could we do that? Sure we could. And if you go to do that, does that make things a little simpler for you? I hope it does, because you're keying in less information. So all you're keying in is really a 47 divide by 201 and then multiply by 10. And you want to do this right now. Take your calculators right now. If you hadn't calculated an answer for me earlier, you need to do this. 47 divide by 201 times 10. And bam, you will get a number. And so that question comes back to, okay, Harpreet, you have a number for me?
Yeah, 2.34 volts.
And 2.34 volts. So now do we have confidence in how this is calculated using a review of voltage divider formula? Now we're going to do the same thing for VR2. So VR2 is going to be equal to what? How do I set this up? If I want the voltage across R2, I would take R2 as the numerator, RT as the denominator, multiplied by VS. Why do I write the formula? I need to see. This is my roadmap. Don't just write down numbers. You just write down numbers is easier to get lost. So this works out to be 980 over, again, 2010. You're going to multiply this by 10. Now, we'll just key these numbers in the calculator. We won't cancel anything here. Just keep it as we see it. So clear the calculator, 980 divide by 2010 times 10, and you're going to end up with a number. So question goes to Gregory. Do you have a number for me now?
4.88 volts.
4.88 volts. Does everybody have that with confidence? VR3 is set up this way. You would want the value of R3 over R total times your VS, and that would be equal to the value of R3, which is 560, divide by 2010 times 10. And when you go to do so on your calculator, and show me on your calculator, because you're going to hold this up to the screen for us to all see. Take 560, divide by 2010 times 10. Pretty basic keystroke sequence. And show me on your calculator what you have calculated. Question goes to Abbas. Show me on your calculator what you've got. All right, and you and go ahead, read off what you see.
2.78607.
Okay. What would you write down on an answer sheet?
We would write down 2.79.
2.79 volts. Okay, everybody okay with all of that? So those are your three voltages using voltage divider formula based on the review of the test questions. Are we good with this so far? All right, so this is good for us to take time and review this. This is something that you should practice more And so how do we get more practice? The easiest way to get more practice is connect with a couple of classmates on the Discord and say, hi, I'd like to practice voltage divider with you. Let's practice this with 4 resistor, or let's practice this with 5 resistors. We're going to state for our team, we're going to have 4 resistors, and each of the 4 resistor values will be blank, 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 with a 22-volt source. And then you all attack it. And then you all compare notes at the end and see how it is that you do, okay? And you'll see how it is that you do. So that's how you can get more practice. You have a marvelous communication tool in Discord. Learn to use it to your advantage. All right. Now, the next question has to do with resistor color coding. And resistor color coding, you are given orange, white, gray, red, red. You needed the coded value, and you needed to determine the minimum, and you needed to determine the maximum. So let me go back to my list. Question goes to Toan. What do you have for the coded value?
387,000 ohm.
The coded value
Plus or minus 2.
The coded value you have as 3, and what was your second digit?
8. 387,000 plus or minus 2%.
Plus or minus 2%. Okay, the 2% is correct. The 00 is correct. The 3 is correct. What's happening with respect to this second and third digit? The second and third digit. Do you have your color coding chart in your
Not
notes?
with me, not with me.
Okay. All right. So here's the thing. Here's the thing, everybody. You have to have your notebook. You should write everything in here. This should always be by your side. Where do you look up your engineering prefixes? It should be in here. Where do you look up your color coding? It should be handwritten in here. You shouldn't have to look for this paper here, look for that paper. You shouldn't have to look it up. It should all be written in here because this is your go-to resource, okay? That way you can be time efficient with your task. So if you don't have it in front of you, we can't answer,
I thought you said don't use the book.
No, I didn't say that. No, because all of our work, as I've said, if you miss that, somehow you miss that, anything that you handwrite in here, you can use on a quiz, you can use on a test, midterm, and final. Anything you handwrite in here, okay?
I understand that. Earlier you said just test it and just try, don't use it. So I try to memorize.
Okay. All right. That's a good spirit. I like the spirit. All right. Let's help us out here. So somebody, when you look up white on your resistor color coding chart, what should that numeral be, my friends?
9.
It should be a 9. Okay. See here, and then the third band, which is gray, that's the one that should be what color? Well, it should be what number, my friends?
8.
An 8. So the first digit of a 3 was correct. This should be a 9 and an 8. The 2 zeros that you spoke were also correct, and then plus or minus 2%. So this is what you work out. Now, for a complete coded value, for the coded value to be correct in proper engineering notation, how would we rewrite this in proper engineering notation? Question goes to Andrew. How would I rewrite this as proper engineering notation?
I just got on here. I'm just trying to figure out what number we were doing.
Can you see my screen?
I can see it.
Okay, so we have 39,800 ohms. So how do I rewrite this in proper engineering notation?
So it would be, let me, I got my calculator here. Let me calculate
Yes.
that real quick.
You punch it in and hit E and G,
Yep.
it magically comes up with it for you.
So it would be 39.8 to the third power.
Which engineering is spoken how?
So a 39.8. Let me get my. Stuck here a little bit. Sorry.
Kilo ohms. I know you just
Yeah,
came.
yeah.
All right, so here, take a look at my paper. This might help you out. We have a convention for all of our values that the decimal point is implied at this location, yes? We also have a convention if you were to receive a check that fell out of the sky, a government assistance check that fell out of the sky, how would this be meaningful to you if this were a government check that fell out of the sky? If this were the decimal point, wouldn't you move over 3 points? Wouldn't you put a comma right here? Okay, and then you'd put a dollar sign right here. Can we relate to this number and speak it if it were dollars in a government assistance check that you just opened in your mailbox? Would this not be 39,000? Yes, and then $800, right? So if we know that we're moving our comma every 3 places from the decimal point, however many numerals we end up with our number, we put our commas in. It turns out that these commas magically align with your engineering prefixes, because in this first comma, which stands for 1,000, that decimal, if we move the decimal point from here to here, we replace that with a kilo, because kilo means 1,000. So the proper coded value of this would be 39.8 kilo ohms, then plus or minus 2%. This is how you would write the coded value for this exercise. Are we clear on that, everybody? Okay, now you have to calculate minimum and maximum. And so some of you may have, so we go back to week number 1, PowerPoint, and I said that I amended this to a newer version and uploaded it into Canvas. So the version we're looking at right now is what you have in Canvas. It does go to show the charges around the subatomic particles. It does go to show the different energy levels, saying that the energy level is higher and higher the farther away you get. It does go to show the outermost band, and it names the outermost band as valence shell. It does go to show an electron that has been freed. How does it free? And right here it says it takes energy applied in order to free the electron. We said there's different ways of applying the energy. We talked about several different kinds of energy. Who remembers those different kinds of energy that we would apply in order to free the electrons? Question goes to Kirsten. Do you remember one of them?
Static?
What, a static?
Just kidding. No, that's not right. Kinetic energy?
You were right the first time. So static electricity is one way. Any kind of electricity would be one way of freeing the electrons. Tony, do you remember another way of freeing the electrons? What other form of energy we would apply in order to free electrons? Do you remember?
Heat.
Heat is good. Ryan, do you remember another one? Is this stuff not written in your notebooks?
I had friction.
Anna, do you remember one more?
Pressure.
Pressure is very good. Pressure is excellent. Dana, do you remember one more?
Electrical?
Electrical? Yeah, that somebody already got dibs on electrical. Electrical is a good one.
Light?
Light. Yes, your solar panels are another way. Light energy will free electrons. Okay, so here's the list. If you look at the list, heat was one way of freeing electrons. Electricity is another way of freeing electrons. Applying a magnetic field is another way of freeing electrons. Light was there. Friction was the most common one. We played with, as when we were kids, playing with the latex balloons and rubbing them on our sweaters and placing them in our hair and such. Chemical is another way. That's how your car batteries work. Your car batteries are chemical. And pressure is another way. So these are 7 different ways of applying energy, 7 different forms of energy to free electrons. And then we go on, it goes on, and goes on, and goes on. And then we had a discussion about your resistor color coding, and you all should have this written in your notebooks. Bad, boys, race, hour, young, girls, but violet generally wins, good sir. If you write that silly little memory tool down, it'll help you with the color sequence without having the color chart. Black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and no band. And then the colors are black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver for these numbers starting at 0 up through 9. And then plus or minus 5, 10, 15, 20%. Or if we use red and brown for our precision resistors, it's 1 or 2%, depending upon whether it's red or brown. So I gave you a handy dandy chart. On calculating, I'll give you 2 slides on calculating tolerances. So in calculating tolerances, you have minimums and maximums. And you could, if, for example, we had plus or minus 10%, you would subtract 29 ohms or add 29 ohms, but I gave you a simpler way. Multiply by these decimal multipliers right here. 290 times 0.9. If you haven't done this, do this on your calculator right now. 290 times 0.9. It equals. Do you confirm 261? Is that a fast way to calculate 90% of 290? It's really fast. How about this? Calculate the maximum, 290 times 1.1. When you take 290 times 1.1, verify you have 319 ohms. That's a fast way to get the maximum at 10%. If you want the minimum in the blue box, the minimum at 2%, that's 0.98 is your decimal multiplier. If you take 3,800, right now in your calculator, 3800, punch it in your calculator, and you multiply by 0.98. Boom, and hit equals. Right there, 3,800 times 0.98. It don't take but a few seconds to push the buttons. It doesn't take you more than half a second to hit the equal key. Are you able to confirm it is 3,724? Or if you put your calculator in the engineering mode, do you get 3.72 kilo ohms? Okay. So where do these decimal multipliers come from? Here's the magic slide. I give this to you on the very last slide of week 1. On the very last slide of week 1, you have a summary of all of the decimal multipliers that very quickly give you minimums and maximums. And all you have to do is multiply your coded value by the appropriate decimal multiplier. And so for minimum, they're spelled out in this column. For maximum, they're spelled out in this column. And if you'd like an explanation where these come from, I can talk to you about where these come from during later on the evening. So I am looking for now the minimum and the maximum for our practice test question. Our practice test question, we coded 39,800 ohms or 39.8 kilo ohms. I would like for you to call out the minimum. Ryan, do you have the minimum, please?
I have 40.6 kilo ohms.
I want minimum.
Oh, minimum? 39K kilo ohms.
All right. 39 kilo ohms would be correct for the minimum. Okay. Anna, do you have the maximum?
40.6 kilo ohms.
40.6 kilo ohms would be correct for the maximum. Okay? Okay. All right. And now let's go ahead and dispense with this because we're done with this. No, actually, don't save. All right, let's come back to here. So back to our potential test questions. Let's see. Number 20, the specific name for a wire across the voltage source terminals. That question goes to Dana. Dana, do you happen to have that answer? The specific name for a wire across the VS terminals.
I'm not sure what the question is asking. Would that just be a short circuit?
That's really good. It is a short circuit,
Okay.
but there actually is one more expression that's even more specific. You called it out correctly. It is clearly a short circuit condition. I'm looking for the specific type of short circuit that we have. Do you remember?
That's short.
It is a dead short.
Oh.
Okay, it's called a dead short. And there's a reason why we call it a dead short. So let's go to here for a moment. Week 2, PowerPoint. And this is up to version 4 because I keep polishing these guys. And we happen to have, let's take a look here. Where did I put it? I think I put it in here. Yeah, short circuits. Short circuits, a common fault condition. All right, a short circuit is where a low or zero resistance wire called what? Called a short is either intentionally or accidentally introduced to your circuit. You don't want these. So here I happen to have a normal circuit, and the normal circuit shows 2 resistors. I have a digital multimeter across the first one, digital multimeter across the second one, and I have an ammeter down below. And I need you to look at how the connections are, because we're going to talk about measuring current very shortly. But as you take a look at this, is the voltmeter, digital multimeter number 1, correctly connected across R1? Answer to that question is a yes. You happen to have here the positive lead of the multimeter is on the positive side of the resistor. The negative lead of the multimeter is on the negative side. The same thing for the digital multimeter number 2. When I go to turn the circuit on, I'm starting off with how much volts do you see on my screen? What do you see on my screen? 12 volts, yes? So that 12 volts is going to be divided. Part of that voltage is going to be across R1. Part of that voltage is going to be across R2. And it turns out we measure 4 volts here, we measure 8 volts here. We need to have predicted this ahead of time. These digits are correct. Then we are asked to calculate current. So in a normal circuit, if we do this, your voltage source is given as 12 volts. Your R total, because there's 1K and 2K, so your total is what? 1K plus 2K is 3 kilo ohms. So 12 volts divided by 3 kilo ohms. Everybody do that on your calculator now. 12 divide, don't just hit 12 divided by 3 equals. Remember to key in kilo. How do you key in kilo? So that would be 12 divide by 3 exponent 3 for the kilo, and then hit equals. And you should verify you have, in engineering notation, 4 milliamps, yes? So take a look at the last multimeter. Look at the last multimeter very carefully, and my circuit on your screen. The negative plate of the voltage source happens to be the lower plate in this case. It's not always drawn this way, but it has been for quite a number of circuits. And the electrons flow from the bottom of this voltage source, yes? Your multimeter for current is placed into the current path. It's not ever, 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 ever do you place it across something. It's always placed in the current path. So let's follow the electrons as they leave the negative plate of the source in the schematic. It flows out of the negative source, comes down here, and this is circuit ground. This is not earth ground. This is a circuit ground in the schematic. So the electrons don't go straight to ground. They will hit this particular node here, go to the right, come down. And where do they enter the ammeter, my friends? Which lead of the ammeter, which port of the ammeter does the electrons flow into? It flows into the negative side, through the ammeter, and then out of the positive side, and then onto the rest of the circuit, okay? And that's how your ammeter should be connected. So in a normal condition, these are normal values: 4 volts, 8 volts, and 4 milliamps. Next, I'm going to introduce a fault condition. I'm going to short between points A and point B. A short is a 0 ohms or near 0 ohms wire that has been introduced either intentionally or accidentally. Let's see what happens here. So if we analyze what happens here with the yellow arrows, the electrons leave the bottom of the source as they did before. They flow down to the bottom wire. They flow into the ammeter, the negative terminal, through the ammeter so it gets a reading. Out of the positive lead of the ammeter, then it hits node B. Well, in node B, I have two paths. The current could split. Part of the current might go to the right. Part of the current will go straight up. Let's see, what does it see when it hits point A? Between point A and point B, if I look straight up, don't I have a bare piece of wire? How many ohms are there on a bare piece of wire? And I said before, you've told me in the answer sheet, 0 ohms. How many ohms do I have going to the right? Well, if the current does come to the right, it comes up, so far nothing, and then it hits here, and then it's got to go through a 2 kilo ohm resistance before it gets to node A. Well, imagine you're driving a bus, and your bus is full of electrons, and your bus of electrons has a choice at point B. At point B, you can take the super warp 9 path to point A with no obstructions in between, nothing, no resistance between point B and point A. Your bus of electrons can go from here to here. Or, if you're the bus driver, would you take that bus and come on this wire and have to go through 2 kilo ohms of resistance before you get to point A? Which are you going to take? Which will get you there faster? The path of 0 resistance, yes? So what has happened here? What has happened here? Look at the words. It says a short has been placed between points A and B. This short will cause the electron flow to, and the key word here is, it will do what with R2? It will bypass R2. R2 will no longer be part of the current path. It's completely bypassed. So all of the current will now flow through this short and only through R1. When this occurs, what's my total resistance in this current path now? The 2 k ohms is no longer part of the circuit after I've introduced this wire. All I have now is 1 k ohms. The 2 k ohms doesn't even factor in now. It's been bypassed. So if I have 12 volts and I have 1 kilo ohms, can you see in the pink box down here how to calculate current? Voltage source is 12. Ohms are 1 kilo. So you take 12 volts, divide by 1,000. What do you have? 12 milliamps. Is this more current than it was a moment ago? A moment ago, what was our current? A moment ago, our current was 4 amps on this slide, yes? Because we had 2 resistors that the current had to flow through. Now, in this slide, once we introduce the short, there's only 1 resistor. And so has the current gone up? The current has gone up. Why is this a problem? If current goes up, the wire will heat up. If the wire heats up, the wire could burn out. The resistor could burn out. So you need to be careful of currents rising all of a sudden, especially because of a short. So this is a short circuit. Now, the next slide is very specific. The next slide goes to show something called a dead short. It is a short circuit. It's a very special short circuit. It's a short circuit that will make your voltage supply dead in just a few moments. And let's observe what happens here. I'm placing a wire across the terminals of the voltage source. Between C and D, I've got this wire. Now look at where the electrons will flow. The electrons will flow down to D. Why would the electrons go through this meter? Why would the electrons bother coming up through R2 and R1? Why would the electrons go to the right when there's 0 ohms on the left coming back to the source? And that's exactly what happens. We have allowed all of the electricity, all of the electrons to immediately leave the source, come back to this side. We have killed our battery. Do not do this to your car batteries, okay? When you go to jump cables and help somebody start their car because their battery's dead, do not take your wires and short your battery will explode. So this is a short circuit, yes. This is a very specific short circuit. When it causes damage to your voltage source, it's called a dead short. Any questions about short circuits versus dead short? Okay, we will close this particular guy. And let's finish this guy up. Okay, calculating these values for number 22, 23, and 24. You've had plenty of time to get these numbers now. Carlos Navarro, do you happen to have number 22?
I do not. Sorry.
Okay. We would hope, let's take a look here. It's all right. So you are given, and let me go and take us off the share. Let me write this stuff down. We want V, and R is equal to 1.6K ohms, and I is equal to 17.54 microamps. And the next one is I, where P is equal to 168.3 microwatts, and V is equal to 18.84 millivolts. And then the last one is R, where V is equal to 23.8 volts and P is equal to 39.28 milliwatts. Okay, let's go ahead and stop the share. And let's go and do this guy real quick and back onto our paper. So with our paper, and the handiest thing for you to have from your notebooks is your 4 circle formulas. V, I, and R, P, I, and V, P, I squared, R, V squared, P, and R. Okay, you just simply look these up in your notebook because that's where these guys should be written. Now let's take a look at each of these exercises. The exercise, the first one, you're given a V. You're asked to find V. V is equal to question mark. What are you given? You're given an R and you're given an I. So you look at these and say, which circle has a V, R, and I? So start on the left. Does this have a V, R, and I, the very first circle? Yes, it does. So you have a formula. If you're looking for the V in this circle, you cover this up with your finger. You take a finger, cover up the V, and you remember that V is equal to I times R, yes? And so this is equal to 17.54 microamps and multiplied by 1.6 kilo ohms. How do you key this into your calculator? And I gave you lots of practice exercises this past week as homework for you to do, so you specifically practice this. In your calculator, the keystrokes should be 17.54. How do you key in micro? The question goes to Chisumaga. How do I key in micro in my calculator?
To key in micro, you would press, you would multiply it by EXP,
EXP,
-3.
and change sign 3. So is it 3? Are you sure?
Yeah, or no, -6, sorry, -6.
Huh. So change sign, and it would be a -6. Okay, micros and -6. And again, you'll find that as you continue through this during the course of the weeks to come, you'll come to remember the millis and the micros as being -3s and -6s. But for the time being, all this stuff should be written in your notebook. All you have to do is flip the page and go to your engineering prefixes and look it up. So you see micro, then you have to key in exponent -6. Then you key in the multiply, 1.6. How do I key in kilo? Question goes to Francisco. Frank? Is your microphone not working, Frank? Okay, we will have some conversations. Greg, how do I key in kilo?
Kilo is EXP3.
EXP3. And then all you have to do is hit equals. Now, when you key in this keystroke sequence, Abbas, what do you calculate?
Do you want me to show you what in my calculator?
No, just tell me what you calculated.
Okay. I got 23.893 E micro A.
You keyed in what I wrote down?
Oh no, I was going up based off. Oh, that's a different question.
You need to stay with us, my friend.
Sorry.
Okay.
I guess my parents have needed a
All right, so the question goes to, all right, so we have, let's go ahead and do this guy together. Let's clear. So what it is that you should have is a 17.54, and you hit your, no, sorry, you can't see it on that side. 17.54, hit your EXP button. It shows you the E, change sign 6, so now you have micro, and then you multiply this guy by 1.6, EXP kilo is 3. Then you hit equals, and when you go to hit the equals key after all of this is said and done, Luis, what do you have?
I have that would be VIR. That is question 24, right?
Question 22.
Oh yeah, sorry. It's a 28.06 millivolts.
28.06 millivolts is what it is we should have. Yes, everybody? Okay, any questions about that for this one? For number 22. So number 23, you are asked for I is equal to a question mark, and you are given power is equal to 168.3 microwatts, and voltage is equal to 18.84 millivolts. So again, you come back to your circles, and now determine what it is that which circle you're going to use. You have a P, you have a V, and you have an I, PIV. Which circle are we going to use? Question goes to Jess. Which circle are we going to use? First, second, third, or fourth?
The second circle.
Second circle. And call out the formula for I for me, please. Cover up the I. What do you have left?
It would be P divided by, or divide P by V. So power divided by
P and divide by V, correct. So we're going to take this number, 168.3 microwatts, and divide it by 18.84 millivolts. And what is it that you calculate on here, Jess?
I got 8.93 nanoamps. Or were you asking for the steps?
Oh, no, I'm looking for the value, 8.93 nanoamps. How many people agree?
The value, yes.
And
The multiple is not quite right.
What were you saying, Kirsten? Is it nanoamps?
Milli?
Would be milliamps.
we got milliamp.
Yeah, there's a difference of a million between a nano and a milli. There's a million spaces, decimal places difference between the two. So let's go ahead and work this out on our calculator. It should be 168.3 exponent. And what power of 10 is a micro again? It should be exponent -6. And then you are going to divide that by, so use the divide key, 18.84. And here you have milli. So you have to hit the EXP again, EXP 3, then hit equals. And when you go to do this keystroke sequence, what is it that you all calculate? It should be the 8.93, but what is the engineering prefix that we should write down? What power of 10 do you see on your calculators?
Can I show you mine? Because I'm confused.
Yeah, no, please. Yeah, let's take a look at your calculator, please.
Let me turn you to the light. Can you see that?
It's kind of dark there. Hold on one sec. It does show nano. Hold on one sec.
I don't know what I did wrong, but
Oh, you didn't. Oh, the 18.84. You didn't put a negative. You did 18.84 E3. It should have been
okay.
-3.
That makes sense. I put as if it was a kilo.
Exactly. You see that? Okay. So if you rekey that in, bingo, you'll get the right answer, guaranteed.
Thank you.
You're very welcome. Very welcome. All right. So yes, then it should be milliamps, okay? All right, very good. And then the last one, let me get a clean piece of paper here. So the last one, we are asked for resistance, R is equal to question mark, when you're given a V is equal to 23.8 volts, and you're given P is given as 39.28 milliwatts. So look at these circle formulas. And let me go back to my speaker view. All right. And as we look at this, look at the circles. You're looking for an R, you're given a V and a P. Which one of these circles, number 1, number 2, number 3, or number 4, has the P, R, V, and a P?
Number 4.
Number 4. And what are we looking for? We're looking for R. So what do we need to do in the circle? You put your finger over the R, what do you see left over?
V squared and P.
Yeah, V squared over P. So R is equal to V squared over P. So the key to all of this is, it's no mystery. You should have these written in your notebooks. You should look at what the givens are. You're given a V, you're given a P, and you're looking for an R. Then you have to decipher which one of these circles am I going to use to find this R. You decide, okay, it's going to be this guy. How do I use this guy? You put your finger over the R, it's equal to V squared over P. Now all you have to do is plug in the numbers. Remember, you always write the formula first. So when you plug in the numbers, it's 23.8. And what are we going to do? We're going to square that guy and then divide by 39.28. And this is a milliwatts. So how do I key this into the calculator? You key this into the calculator as 23.8, and you find your x squared key. That's your square key. And then you can hit your divide function and then take 39.28 milli exponent, change sign, and milli is what power of 10? -3. If it isn't second nature, it's okay. Look it up in your notebook because all your engineering prefixes should all be there. Then you hit the equal key. You follow this keystroke sequence. And the next person calling out this answer shall be Harpreet. What do you have as an answer for us for number 24?
I think I got the wrong answer. It's a 14.
Follow this keystroke sequence with me right now. 23.8. Find your square button. Then hit divide. And then key in 39.28. Hit your exponent -3. Boom, enter. That's how long it takes to key into your calculator.
495.04.
495.04
kilo ohms.
Kilo ohms. How many people agree with 495.04 kilo ohms?
No.
No. No bueno.
No.
Did we miss something in the keys? All right. Which calculator are you using, heart rate?
The same one you got right there.
Good. Okay, so we're going to key in. We clear. So you have 23.8, and you find your x square key, which is right there. It's its own button. So you square it, and then you divide by 39.28 exponent negative 3. And then you hit equals. And then you hit engineering. And so what do you have when you recalculated this, Harpreet?
11.42.
I don't think so. Do you see what I have on my display?
Yes.
How many people agree with 14.42 kilo ohms?
Yeah.
Yes. And how you got something else we'll have to talk about in a moment. Okay, everybody, you're on a quick 10-minute break. We're done with the review of the potential test questions. Everybody take a quick 10. I'm going to put a timer on. And while we have the timer on, Harpreet, let's talk about this calculation because I'm concerned that you've done it and haven't gotten.
I figured I keyed in wrong.
What did you key?
I think I doubled the square. I did a 23.82 4 times. So, give me a second. So I got it right now. I keyed in right.
Prove it to me. Let me see your calculator. Hold it up to the screen. Harpreet, where are you?
I'm here.
There you go. Now, hold it steady. Ah. Okay. That's better. All right. So, yeah, you got, now you feel better. I feel better that you feel better because at this point in time, we should not have these kinds of calculator issues. So while we're on break, if you haven't stepped away, does anybody here have any questions for me? We can use this break time for a quick Q&A.
What was the answer for number 21?
The answer for number 21, let's take a look here. Oh yes, you either have an auto scale or a manual scale digital multimeter. There's only 2 types of multimeters, either automatic scale or manual scale. And let me show you what those look like. So, here we go. Cool. All right. And speaker view. And so you can see I have 2 digital multimeters on my screen. Focus. The one on the left is auto scale, meaning all I have to do is switch it to AC voltage or DC voltage. Here I have a range of DC voltage values I can select. I can go all the way down to 200 millivolt scale, 2000 millivolt scale. So I have different scales. And so when I can select this way, this is called a manual scale. Here, there's only one setting for DC voltage, and it will automatically shift the decimal point, kilos and megas appropriately on the display. So those are your 2 types of digital multimeters, manual scale versus auto scale. Did that answer your question for you?
Yes, thanks.
Cool, you're very welcome. All right, other questions? This is a good time to ask.
I have a question.
Yes, please.
So for the sheet that we just went over on question 18, I was not using the voltage divider formula to find my answers.
And you don't have to. Were you using VIRP? Were you using a VERP chart?
Yeah.
Yeah, it works.
I was just wondering, for the voltage divider formula, is that new or did I miss that in a different lecture?
No, that is not new. You might have missed it because it's in our recording. I did use voltage divider in, I think it was last Tuesday. Let me see if I can.
Okay.
Yeah, because we had an exercise. Let me pull it up.
I'll go back and review I have been watching last week's already,
Yeah.
but I will look for that specifically.
Yeah, let me see if I can help us find it too here, because I had an exercise. Engineering notation, here. Yes, is it one of these?
I can only see the desk.
No, yeah, I'm finding it first.
Okay, cool.
Yeah. Okay, yes. Let me go ahead and share this with you, help you locate it here and here. All right, so last week's, we happen to have had, let me go back a few. We happen to have started here, digital multimeter. We talked about ammeters, voltmeters, ohm meters. And then we talked about how the connections were made for voltmeter. There were very specific directions on how to do that. Ammeter, even more specific, which we'll talk about further this evening. And then we have ohm meter, how to do that and what to do, what not to do, polarity concerns. And then we had the circuit analysis. We did this together. I introduced this as a very simple circuit, simple series circuit. We talked about voltage divider, and we did these calculations here using voltage divider formula. So the voltage divider formula is shown in the general form. VRX is equal to RX over R total times VS, exactly as I wrote on the paper earlier. And then we did each one of these individually. So as I have 3 resistors and they total up to be 650, then the first resistor is 300 over 330 over 350. We calculate 2.54 volts. And then we calculate this voltage for VR2 and this one for VR3. And how do we know these were done correctly? If we add these voltages, they all add up to 5. Okay. So yeah, this was part of last week's discussion in this part of the PowerPoint.
Okay.
And whether I talked about it could have been part of Thursday, it could have been part of Tuesday. I don't remember whether it was Tuesday or Thursday, but I updated the PowerPoint so that it is now presently version 4. It is the most up-to-date of last week's, and that already has been uploaded into Canvas.
Awesome. Thank you.
You're very welcome. Anybody else with other questions while we have a few more minutes on our break?
For the test, is it going to be like similar in length to what we just did, or should I expect it to be longer?
It should be similar, if not shorter.
Okay, thank you.
Because I would hope that you all would have had plenty of practice to be able to use your notebook, refer to your notebook, have all your formulas, have all of your engineering prefixes, have everything here. So you don't have to flip paper thing. Just refer to your notebook for your quick and answers. You might even put Post-its in there or some other kind of colored tabs to quickly find something if you're looking for something. So whatever you put in here, this is your quick reference, and you should be able to get through the exercises pretty quickly. Certainly the calculations. The theory side, yeah, you're going to have to pay attention to what we're doing in our PowerPoints and our lectures. So I don't anticipate it will take as long. And we took over an hour because there was a lot of questions and a lot of explanations. But on a real exercise, you would turn in your paper at the end of half an hour and let's see what you got. So as we take a look at the slide in front of you, you are reintroduced to parallel circuits, the characteristics, and its formulas. There is a matching version of this pertaining to series circuits. And on the series circuits, there happens to be a bullet point list of characteristics, and there also happens to be a bullet point list of formulas. On the parallel circuits, same idea. There's a bullet point list of characteristics and a bullet point list of formulas. So let's go ahead and take a look at what's new and exciting in front of us. It says here, parallel circuits divide something. What do they divide? They divide current. Parallel circuits are known as current dividers. What is the same across all branches of a parallel circuit? Voltage is the same. And the largest ohmic resistance will flow the lowest amount of current, and the smallest ohmic resistance will flow the highest amount of current. It says here the currents are proportionally distributed through the parallel branch resistors. Circuit will be cut off if there is a break in one of the branches, like the new Christmas tree lights. These are your characteristics. You should write them down in your notebook, okay? Just to have as a handy reference. I highly recommend it. Then you should also have the formulas. And let's take a look at the formulas. The formulas are interesting. They show that the voltage is equal to the voltage of the first branch, equal to voltage of the second branch, equal to however many branches we have. So take a look at my schematic. If you take a look at the schematic that's shown, you have a 9-volt source, you have 3 resistors, R1, R2, R3, 10 k ohms, 2 k ohms, and 1 k ohm. How much, well, let me back up. The top of these resistors, the top of these 3 resistors are all hooked up to the positive side of the source, yes? The bottom of these 3 resistors are all hooked up to the bottom of the 9-volt source. Therefore, this 9-volt source is the voltage that is across R1. It is also the voltage across R2. It is also the voltage across R3. This is what's known as parallel. The voltages are all the same in the branches of a parallel circuit, but the currents will not be. The currents will split. And so take a look at the current. The current formula says the total current, I total, is equal to the sum of each of the individual currents. How is this different from series circuits? In series circuits, remember you found one current and weren't all the currents the same? Here, the currents are not the same. The voltages are the same. The currents add. Interesting. And we'll work out some examples of this to help you understand better. R total, you're given a really interesting formula. It looks very intimidating. It's actually very easy. We'll talk about that in a little bit. Take a look at the power formula. Now, if you've taken the time to write formulas down from the last time this is not the first time you've seen this slide, you were shown this last week. And hopefully you have written this stuff down in your notebook. If you compare the power formula for series and the power formula for parallel, it's the same thing. The total power is equal to the heat dissipated by the first resistor, add to the power of the second, add to the power of the third. It's the exact same formula. Then you have something known as CDF. CDF is current divider formula. Previously, we had a VDF, so now we have a CDF, which is current divider formula. And the current divider formula is set up as a fraction, the same way voltage divider was set up. Here, if you're looking for a current, IX for some branch is equal to R total over RX times the total current. We'll hold that thought. We won't play with current divider formula till next week, but all the formulas are shown to you here. Next slide is even more revealing. Here are some definitions. The parallel is defined for you here. This is what you need to have in your notebook. And read this with me. It says right here, parallel, devices are in parallel if and only if. That sounds like we have a very specific condition. It doesn't say maybe. It says if and only if. What happens? It says the leads on one side of these devices meet at one common node or a point. Then you have this word in here. What is this word? This word is and. It doesn't say or, it doesn't say sometimes, it says and. This is very absolute. You have an if and only if, you have a condition 1, and you have a condition number 2. So as you look at this, what's the second part? The leads on the other side of these devices, what? They meet. Where do they meet? At a different common node. Very interesting. That's the definition of parallel right there. Then you have these other ones, which I'll talk about in a moment. But let's take a look at the definition, and let's look at the schematic that were presented. Are the upper leads of these 3 resistors connected at one common node? Is the top of R3, can I call that A? Is that connected to the top of R2? Is that also A? Yeah, there's no resistor between them. They are the same node. And is the top of R2 connected to the top of R1? Is that also point A? Yes, it is. It's one stretched out point. Also point A. And is that connected to the top of the voltage source? Also identified as A. Guess what? This line across the top of these resistors are all one giant node that they share. So far, have we satisfied the first half of the definition, part 1? Do the leads on one side of these devices meet at one common node called A? The answer is yes. Does that make them parallel? Not necessarily. We have to satisfy the second condition. The second condition says what? If you read the definition, which should go in your notebooks, the leads where? On the other side of what? These devices, so meaning the lower leads, do they meet at a different but common node? And let's take a look at the schematic. If you take a look at the schematic, does the lower lead of R3, R2, and R1, do they all meet at this giant node stretched out called node B? They are all node B. The entire bottom wire is node B. It's one stretched out node, okay? That is your definition of parallel. If it satisfies these 2 sentences, you have parallel. If it doesn't satisfy these 2 sentences, you don't have parallel. And for many, many circuits, for many illustrations, a lot of authors show this in a ladder. It always looks like a ladder. I'm going to show you something that doesn't look like a ladder that will cause you to think a little bit more in a little bit. Then there's also, as series circuits have a nickname. What's the nickname for series circuits? I've shared this with you before. Strings. Parallel circuits have a nickname. What are parallel circuits nicknamed as? Banks. So this is a bank of how many branches? A voltage source with 3 branches. So a parallel, number 4, a parallel circuit will resemble a ladder where the rungs are called branches. So in the very first branch, I happen to have 1 resistor. I could have more than 1 resistor in that branch. I could have 2 resistors in this branch, 3 resistors in series in this branch. But as it exists, this is a branch. Then, the number 5, our total, and here's the key thing, our total for parallel will always be less than the lowest ohmic branch. Are you getting this sentence? If I want the total for these 3 resistors hooked up this way, it will always, always, always be less than the lowest ohmic branch. What is my lowest ohmic branch of these 3? 100 ohms. And my R total will be less than 100 ohms. There's a reason why. And I'll show you how that calculation is done. Also, very easy. Okay, next slide. You're introduced to the reciprocal formula. This formula that looked really intimidating a little while ago. It's not so intimidating, but I have some things to share with you, and that is something called the tap and something called a node. Ever see I've tap and node in 2 parts of this particular PowerPoint slide? I have tap and node here, I have tap and node here. Who can point out what you see as a difference between a tap and a node? Somebody take a stab at this. And you all should turn on your cameras.
Yep.
Javier, yes, I'm so glad you signed on. All right, so what do you see as a difference?
one connected or one not?
One is connected and one is not. That's a very good observation. What else do you see as a difference between a tap and a node?
One is connected to the voltage source and the other one's connected to other components.
There is no voltage source in this slide.
My bad.
In a circle?
No. It's okay. It's okay. So here, let me give you the definition, and this is what you should write down in your notebooks or somewhere for now that you transfer to your notebooks. A tap equals an open point of connection. It is simply an open point of connection. We're going to connect something to it. What are we going to connect? Probably a meter. So if it's shown as a circle that's not filled in, and the tap you can see is a circle that's not filled in, it is called a tap. That means I can hook something up there. It's prompting me to hook something up there. What is it that I'm likely to hook up there? Will probably be a meter in this case. So that's the definition for a tap. Tap is open point of connection. Node is a circle that has been filled in. And node, you want to write down, is closed point of connection. Closed point of connection. Okay? So it's the difference between a tap and a node. Everybody got that? All right. So the formula, if we take a look at the formula together, it shows RT is equal to 1 over a big numerator. It's kind of a scary looking numerator, but look the numerator up. It shows 1 over R1 plus 1 over R2 plus 1 over Rn, however many resistors we have. Let me show you in the black line how easy this is to determine. First of all, on your calculators, you want to find your reciprocal button. Find on your calculators your reciprocal button, okay? So on your calculators, and if all of us are using the same calculator, the reciprocal button is a x negative 1, okay? It's an x negative 1 and it sits right there on your calculator, x negative 1. That's your reciprocal button. On some calculators, it is known as a 1/x. 1/x. So I show it to you that way. So those are the two most plausible buttons that people will use for something called reciprocal. Everybody should repeat the word reciprocal. 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 Okay? You get used to speaking it, you'll be able to speak it with greater confidence when you're facing the interview. So here we go. What we're doing in the black, if you follow this, R1 is 20 ohms. R2 is 40, R3 is 30. So those are the three values for this circuit on the left. I got 3 resistors in the drawing. They are in parallel with each other. I have a tap at the top I can hook up to. I got a tap at the bottom I can hook up to. I need to predict what the ohms are to begin with. What's it say in black? In black, it shows my RT is equal to 1 over divide by, in parentheses or brackets, 1 over 20 plus 1 over 40 plus 1 over 30, close brackets, close parentheses, equals some value. Now that's what I would write down. Now on your calculator, it's much easier. On your calculator, follow the blue type, the blue letters. It shows 20, and then you hit your reciprocal key. I'm going to do this with you. Clear, turn it on. So 20, hit the reciprocal key. What happens after you hit the reciprocal key? You add 40, but after you hit 40, what do you see on the slide? You have to hit the reciprocal key again. And then you hit add, then you add the 30, you hit your reciprocal key again. Now there's no more add after this because that's the third resistor. You simply hit equals, then you hit reciprocal one more time, and then you hit equals. And then you may or may not have to hit engineering. In this case, you don't. Do you end up with the same number I have on my calculator? Can you see that in my little screen? I want to keep this on the PowerPoint slide, but if you can see where all your friends are at, I have 9.23 with exponent 0 zeros, meaning I end up with 9.23 ohms. You need to do this with your calculator, okay? So you get out your handy calculator and see what you can do. Are you able to get this calculation? Do it now, giving you a moment to practice using the keystroke sequence of the first set of blue numbers. I've got 3 resistors, 20 reciprocal plus 40 reciprocal plus 30 reciprocal equals, hit reciprocal and then hit equals one more time. You should end up with the 9.23. So everybody hold up your calculators to the screen and see those numbers clearly on your screens. Fancy, nice, wow, we've got fancy TIs in here too. Very nice. Good job, okay. Very nice, I see, nice. Thank you,
It's
Louise.
different.
It's all right, so Jess?
Yeah.
Yeah, that's all right. We will get it. We will get it. It's the first time we're doing this. So let's see. You're using, good old TI-83. That's a marvelous calculator. Okay, so on a TI, what you do, turn it on, clear, and your reciprocal key happens to be on the TI right there, the X-1.
I was using that one, yeah.
Okay, so what you do on the TI is you key in 20 and you hit the reciprocal key, then you hit the add, then you hit the 40, you hit the reciprocal key again, and then you hit add, and then you hit the 30, you have to hit the reciprocal key again, then you go to hit enter, then you hit reciprocal, and then you hit enter one more time, and it should come up for you like this. Let me get the right font.
After I hit enter, you hit reciprocal on the answer and hit enter again. Okay.
Yes.
I skipped that part.
Yeah, at the end, yeah, if you skip that, you'll end up with some decimal number, some milli something, or micros.
Also, there's a cat. I feel like I need to point out the cat.
Yes, yes. That's it. So, you know, we're doing something new, and that's how it is. So does everybody feel comfortable with how to make that calculation? It's not a hard calculation. Like I say, the formula looks more intimidating than the actual work itself. Let's try the next one. Take a look at the next one. The next one shows 980, 470, 680, and so you throw that in the reciprocal calculation, and so the keystroke sequence is identical. So take a look at the bottom of this slide, and it shows 980. You hit your reciprocal key. I'm going to do this with our simple calculator. So I'm going to take 980, hit the reciprocal key, then hit add. And then I'm going to take 470, hit the reciprocal key, and then hit add. And then I have 680, hit the reciprocal key, no more add. I have to hit equals, then reciprocal, then equals. And then in engineering, what is it that you have? Show me on your fancy calculators. It should look like mine right here. Yes? Oh, look at that. Look at that. Nice, Greg. Nice, Andrew. Nice, Ryan. Luis. Very nice. And Javier. Very nice. Harpreet. Very nice. There you are. Oh, that's my calculator. That's very nice. Yako. Abbas. Very nice. Very nice. Good job. Dana, Erica, you guys okay with this calculation? Tony, you all right with that?
Yeah.
Nice. Very nice. Cool. Okay. All right. Well, that's it spelled out for you. Reciprocal will always work no matter how many resistors you happen to have. If you happen to have 2, 3, 4, 5, 10 resistors, you can always rely on reciprocal formula. Now, how about some shortcuts? How many of you like to work smarter, not harder? I do. So let me show you the shortcuts. Here's a shortcut for parallel circuits. And these are for very special circumstances. Look at the one on the left. The one on the left says R total for equal value resistors. Take a look at the circuit. The circuit shows 3K, 3K, and 3K. Are they all the same value? Yes. How many of them do we have? 3. All you have to do for equal value, same value resistors, is just divide those ohms by the number of resistors. So what is 3 kilo ohms divided by 3, my friends? 1 kilo ohm. That's a marvelous shortcut. You didn't even have to touch the calculator for that one. That's called working smarter, not harder. How about the example below? In the green box. In the green box, I've got 3 resistors. Again, are they identical value? The answer is yes. How many of them do I have? The number of resistors, N, is 3. So what is the method? I take the R value of 6 ohms and divide by 3. What is my total resistance? 2 ohms. Is that remarkable? Is that fast? Is that a heck of a shortcut? You're welcome. Now, take a look at the one on the right. The one on the right is specific for 2 resistor banks. And it's a method called product over sum. Product over sum is simply we multiply the 2 values and divide by the sum of the 2 values. So take a look at the first box I have on the right-hand side, 20 ohms and 40 ohms. What do? You take 20 times 40, hit the equal key, then you divide by, open parentheses, 20 plus 40, close parentheses, equals. And you have to do this keystroke sequence exactly as I show you, okay? It has to be done exactly as I show you. Otherwise, you're going to end up with a different number. And don't say, oh, I forgot to hit the parentheses. Oh, I forgot the first equal button. If I put it on here, you've got to type it in your calculator. Try this out, product over sum.
Do we show you our calculator when we're done?
No, in a moment you'll show me something else. But this is fine. Do you feel comfortable with this product over sum? If you're not getting these numbers, I can explain to you what you're doing, and I can help. If you're not getting these numbers and you're not asking for help, I can't help you, and I really want to help you.
Can you explain that again?
Which one? Product over sum?
Yeah, the keystrokes.
The keystrokes. Okay, and let's look at the first set of blue, and I will show you on my calculator in the inset. So you should be able to see my calculator on the inset. I'm going to clear, and looking at my calculator, looking at the keystrokes, it says I should do 20 times 40. Yes, so I'm going to do 20 times 40. Well, what happens after the 40? What do you see in my notes? What does it show you? Greg, read it to me. What's it show you?
Equals.
Equals. I have to hit the equal button. If I don't hit the equal button here, my calculation is going to be messed up. Then what's the next thing you see after the equal sign?
/,
which is a divide. What do you see after the divide?
Parentheses.
And on your calculator, the parentheses are located right above the number 9. You have an open parentheses on the left, you have a closed parentheses on the right. So you have to hit the open parentheses, then you do 20 plus 40, then you close parentheses, then you hit equals. And when you do, you might have to hit engineering. What does your calculator show you?
13.33 ohms.
Yeah, 13.33 ohms, okay? So that's the keystroke sequence. You do have to hit everything that I put on there. You can't come back, I got the wrong number. Oh, I forgot the first equal key. Oh, I forgot the parentheses. No, it's printed there. You got to follow it to the button. And as long as you do, it works. But here's the thing. For the shortcuts, these are considered shortcuts, yes. But could we calculate all of this using reciprocal formula? Yes, you betcha. Everything on the left, the kilo ohms, the 3 sets of kilo ohms, the 3 sets of 6 ohm resistors, and everything on the right, the 20 and 40 ohm, we could do all 3 of these circuits using reciprocal, and it would work. It would give us the exact same answer. So if you don't want to play with shortcuts, you can always use reciprocal and get used to using one method. It will always work. Here's the practice. Practice. Here we go. Let's go. First one. Do it. Do it now. Hey, hey, Luis, look at that. Look at that. Andrew, look at that. Looking good. Yeah, you finished the first one. Javier. Yes, nice. A little more closer to the to your camera. Greg looks good. Hey, that looks great. Harpreet, looking good. Abbas, looking good. Ryan, nice. I think you're getting it. Toan, nice. Tony, Chisomaga. Just look at that. Hey, hey. Fantastic. Let's try the second one. And yeah, that looks good, Andrew. Looks nice. You get a rhythm going, you know, with the sequence. Harpreet looks very nice. I see that. Good job. Ryan looks really good. Greg, oh, that looks great. Tony, hold a little, tilt it upwards. There we go. I can see better now. Yeah, perfect. Thank you. Carlos, looking good. Abbas, nice. Very nice. Good job, Carlos. Tony, nice. Let's try that third one. Toan, yeah, I saw that. Yeah, that looks good. Ryan, all right, smoking. Do we have the kilo at the end? Good, I can see the kilo. Jess, do we have the kilo? Oh, that's the second one. That's good, Jess. Luis, yeah, looking good. Like that. Great job. And yes, very nice, Greg. You're on it. Nice work. Tony, yeah, perfect. I can see that now. Thank you. Looks nice. And Luis, that's good angle. I can see that. Thank you. Is everybody developing a comfort level with the keystroke sequence for reciprocal formula? That's what you get to practice for parallel circuits. I'm not having you do Ohm's law. I'm not having you do any other calculations for parallel this week, only to calculate our totals. Okay, that's all you gotta do. And you got a lot to do. I mean, you got a few more to do, but that's all you're doing with these calculations. So let's take a look at the next slide. The next slide goes to show more practice. And you take a look at the one on the left, you say, well, wait a minute, Co, you got something that's kind of a crooked ladder there. Are you sure you're giving me a parallel circuit here? It doesn't look like a ladder. No, as I said, not all parallel circuits look like a ladder. But is it parallel? So let's review the definition for parallel. If we go back to the definition for parallel, do the upper leads all meet at a common node? Does the upper lead of the 33, the 27, and the 20, does it meet at a common node, yes or no? It does. That's half of your definition. How about the lower? How about the second half of the definition? Do the lower leads meet at a common node? Well, the 33 comes down to this dot, this node. The 27 and the 20 comes down to this dot. It looks like we got two different nodes. Wait a minute. Is there a resistor between these two nodes? The answer is no. This is one huge node that's just spread out. So our 20, the 20 ohm, the 27 ohm, and the 33 ohm are all connected with no resistors between them. So even though this is not drawn in the traditional ladder illustration, these are still parallel with each other by virtue of the definition we cited earlier. And the definition was given to you here. Leads on one side meet at one common node, and the leads on the other side meet at a different common node. Okay, and then we end up with this. So here's the thing that might help us out a little bit. Let me come off of this particular guy for a moment. Stop this and let's go back to the camera. And then on the camera, here we go. If I happen to have this guy here, and then I happen to have a resistor here, and one coming up here, and one coming down here, and then I have a node here, and I got a tap, and I got a tap. We're going to use an ohm meter. Hook up between this point and this point to do the measurement. And I'm going to show you that clearly using green, these resistors at the top meet at one common node, yes? Now take a look as I show you in red, the lower leads also meet at a stretched out but still common node. This is one big node that's stretched out like that. And they are connected at the bottom in this way. They are connected at the top in this way, which makes them truly in parallel with each other, even though it is an unconventional drawing. Okay, so that might be one other way to help you out. Here's another way that might be able to help you out. I've done it with this before. I don't know if I can do it here, but if I take 3 pens, okay, I have 3 pens that I'm holding between, come on, Co. Try to do it this way. All right. I've got 3 pens between my 2 hands. What is their electrical relationship? Well, are the tips of all the pens touching my left hand? Are the buttons of all 3 pens touching my right hand? If these guys were resistors, they are electrically in parallel with each other. But wait a minute, this looks nothing like a ladder, okay? In fact, if I hold it at this angle, it's kind of, looks like maybe they're monkey bars, okay? They're certainly not a ladder, and it's certainly not all in one plane. So as you can see, this is a kind of a tripod arrangement, yes? So are these in parallel as I'm showing you in the camera? Now, how about if I do this? I do this. I fan them out. Oh my goodness, this is certainly not looking like a ladder, but again, does it satisfy the definition for parallel? Are the tips of these pens meeting at one common point, and are the buttons of these pens meeting at a different common point? Now this looks nothing like a ladder, but are these, if these were resistors, are these electrically in parallel with each other? The answer is yes. Why? Because it fulfills the definition, okay? So just don't get too used to looking at beautiful ladders, because they can be looking, you could be looking at parallel relationships a number of different ways. You just have to always go back to the definition. All right, so let's come back to this share and let's finish up these calculations. Let's go, quick. 3 resistors again, practice. 27 reciprocal plus 20 reciprocal plus 33 reciprocal equals reciprocal equals, and Harpreet, glare, still glare, better angle. Okay, I can see that. Good. Greg, good. Luis, good. Tony, good. Try the second calculation if you've got the first. Kirsten, good. Andrew, good. Very nice. I think you're getting the hang of it. Chisamaga, tilt it up. That's good. I see that now. Perfect. Thank you, Chisamaga. And Ryan, I see that. Good. That's also very nice. Carlos, look at that. Wait, background. There you go. Perfect. I see that. Nice. Now try the next one. Harpreet. Oh, look at that. You're speedy. Nice. And Tony. Very nice. Greg. Look at that. Good job. Got that nice little exponent 3 at the end. Abbas. Nice. Are you using the calculator we found together? Abbas? You found a different one? I can't hear you. It's okay. Luis? Looks good. Andrew looks good. Yeah, I was chatting with Abbas earlier in the weekend, and we were talking about calculators, and we found this great one for an iPhone. It's absolutely magnificent for free. Pretty good. Ryan, nice. Very nice, Ryan. And Tawan, Carlos, good. Tawan, tilt it more upright so I can see the numbers. Chisamaga looks good. Carlos looks good. Okay, I see that now. Tawan, good. Jess looks great. Dynamite. Dynamite, dynamite. I think you got the hang of it. Cool. Okay, we're done with this for now. You have plenty of exercises for calculating, to practice calculating parallel in your homework. I need to talk to you now about current circuit analysis. So we had the circuit that we analyzed for voltages last time, and our task now is to think about how electricity flows in the circuit. Electricity flows in the circuit from, electrons flow from the blue rail, from the negative rail, through the jumper at point D, through this orange jumper, and I'm labeling that ground, to point D on this side, because you see on my schematic, I did the ground symbol here. And then I have my first resistor. My first resistor, could I have skipped putting in the jumper? Could I have connected my third resistor to my second resistor? Could I have hooked them up together end to end without using a jumper? Sure, I could have, but I find the circuit building easier to understand if I put jumpers between. So I have a jumper point C connecting R2 and R3 together. Then I have a jumper at point B connecting R1 and R2 together, and an RA at the top of the schematic. And the first resistor jumps over the orange jumper to point A over this side, which goes to my positive rail to the positive side of the circuit. Everybody, you've seen the circuit before. What is the thing that we want to remember here is that current is the same in all parts of what type of a circuit? Of a series circuit. Well, we calculated this using Ohm's law. 5 volts divided by 650 is equal to 7.69 milliamps. Could everybody do this calculation right now? 5 divided by 650? And you should be able to confirm 7.69 milliamps. Yes? Cool. I see that. Yay, Harpreet. Good job. Okay. So you have 7.69. But here's the thing. We said that in a series circuit, we said, look at that. Good job. We said that in a series circuit, thank you, Carlos. Good job. We said that in a series circuit, the current is the same throughout all parts of the series circuit. That means we should be able to measure through, we should be able to confirm through measurements this 7.69 milliamps flowing through jumper B, through jumper C, and through the jumper wire at ground. Because one of your homework questions asked, when you use a voltmeter, how many points do you measure with a voltmeter? You measure at 2 points. How many points do you use to measure resistance? You measure at 2 points. Current, the definition for current says that it is the rate of flow of electrons past a single point in your circuit, okay, past a single point in your circuit. So current flowing through 1 point in your circuit. We have to decide what point that is in our circuit. All right, here we go. We're going to review our ammeter connections. And as we review our ammeter connections, you've seen this slide before. We're going to go back into this in detail. You have to read everything to the letter. It says, number one, first bullet point, you have to connect the probes appropriately to the digital multimeter, red to the milliamp port, black to the common port, because on a number of meters, they happen to be different. And depending upon the meter that you have, they may be different. So let me show you back onto the camera exactly what we're talking about. So let me go back to the camera and let's go to here. And for those of you who were on break earlier, you may have missed this part of the discussion because someone had asked. I thought I'd answer this question. It was also on our review question set. What were the two different types of multimeters? The two different types of multimeters are, come up here, manual scale versus auto scale. So let me go ahead, stop the share, and let me come to here. Okay, so now you can see, let me focus. Cool. So this is an auto scaling multimeter. If I simply go to DC volts, all I have is one position for DC volts, and it will automatically scale the reading for me. This particular meter is manual scale. I have voltage, DC voltage on this portion of the meter, 600 DC, 200 DC, 20 to 200 milli. I manually adjust the scale on this multimeter. This one does it automatically. Is one better than the other? No, I like both, because there's sometimes certain auto scaling that just doesn't happen quite the same degree of resolution as if I do this manually, okay? So given that, the next thing to make note of is the connections. We said that the connections for current are very specific. So here I have another multimeter, and you have your multimeter jacks, and normally the red and the black jacks go into, the black goes into common, of course, and then this one goes to where you have volts and ohms. And we said to set this up for current, you have to take the red lead out of this position and you have to put it to where it says milliamps, because this one has 4 ports on this particular multimeter. I happen to have volt ohms here, common, milliamp, and 10 amps over here. So black will always go to common. And if I want to set this up in the milliamp mode, then I take this red probe from here and I move it over here to milliamps. First thing I got to do is make sure my probes are set up properly. On this particular meter, this one is interesting because if I pull these out, there's only 3 ports for my bananas to go in. My common, so I take my black and I put it in the common. But this one here, I can measure volts, ohms, and milliamps. I don't have a separate milliamp port. I have a separate 10 amp port, but a separate milliamp port, that's all the same. So I can just leave this guy where it is. Not all meters are set up this way. Here's one that's very interesting. This is a Fluke. It's one of the best in the industry, but this particular model is not designed to measure current. So I don't have a current measuring position on this particular multimeter. And then for the one that has the broken fuse, this one is also set up this way. This is volts, ohms, and milliamps. So black goes here, red goes here, and then and then another one here, same thing. Common goes here. This port here is for volts, ohms, and milliamps. So interesting for some of these. I don't have to make any switching of the cables. The cables and their positions for volts and ohms also happens to be for milliamps on this multimeter and this multimeter. But where they are not, if they are not set up that way, if they happen to be set up as they are on this multimeter, you got to make sure to switch the red to where it says milliamps, or we're going to have issues. Okay, so the first thing you do according to the slide is you want to set it up for the set the probes up appropriately. And let's go to here, and yes, okay. Then the next thing you do, you have to select the scale. So if the scale is automatic, you just set it to milliamps. If it's not automatic, you have to dial into the specific range. Then what do? You have to decide where to create the open. There's no ifs, ands, or buts about this. You have to decide where you want to measure. What point in the circuit do you want to measure the current? You have to make a decision. Once you make that decision, then what do? You then connect the probes. You create that open, then you connect the probes into the open to be measured. Be mindful of correct polarities. Red to the positive side, black to the negative side. Then you turn on the circuit, then you turn on the digital multimeter, you record all the numbers from the display, no rounding off. Then, it says the polarity sensed by the red probe, as we read it towards the black probe, is the polarity recorded in the current reading. Next bullet point, current is always measured between 2 points of the open. The open is 1 point in the circuit, but the moment we pull that jumper wire, we have created 2 connecting points. And then after it's read, you turn off the multimeter, you de-energize the circuit. Now we're going to do this together. So, oh, yeah, before we do this, there's forbidden. This is in red and yellow. Forbidden connections. You never, ever, ever, ever connect your ammeter probes across sources. Why? You're going to blow a fuse. You never ever connect your ammeter probes across your resistors or other devices in the circuit. Why? You might blow a fuse. Why? The fuse you blow is not very expensive. Well, it's only 50-cent fuse. But here's the thing. If you have to acquire this fuse, it's going to cost you way more money to find where this fuse can be had. Then you got to go and buy it. Then you got to take the time to open up your multimeter. And on some of these multimeters, you have this really, really nice rubbery jacket around the meter that protects it. Then you got to peel off the rubbery jacket to get to the meter. Once you get to the meter, then you got to get a screwdriver to pop open the screws. Then you open up the blasted thing. And then you say, oh my gosh, there's 2 fuses. Which one is the right fuse? Then you have to figure out which one's the right fuse. So everything said and done, you really don't want to blow your fuse. Okay? So as long as you follow the directions carefully, you will not blow the fuse. You'll be a happy camper and your ammeter will continue working beautifully. Looking at the circuit, it says we will confirm that the current is flowing through all parts of this the same. Okay, it's a repeat of the previous slide. Now, I'm going to measure current at point B. Everything that I've typed on the left-hand side here is the same as this slide here. I've just copied it, but now I just want to bring it back to where we see this. Point B's jumper has been removed. There was a jumper at point B joining resistors 1 and 2. Here's that jumper. Everybody see that red jumper right here? There's a jumper between R1 and R2. I'm deciding I want to measure the current at point B. How much is flowing through that jumper? I pull it out. I will create an open. There is no more jumper here now. But I have 2 probes. I have a red probe and I have a black probe of the ammeter. Now, I could use my standard probes and stab at R1 and R2, or if I happen to have alligators, if I happen to have hooks, then I could use little pins, and that's what I've chosen to do here because it gives me a cleaner photograph. So I'm using pins, but I am measuring with the red probe at the bottom of R1 and the black probe at the top of R2. So what's happening here is the electricity, the electrons flow from this blue rail, yeah? The electrons flow here through this yellow jumper, through the orange jumper down here, down through R3, and then it flows up through R3 to this jumper through R2. Now watch what happens. The electricity will not go to R1. What happens to the electricity? It follows this row 12, to this pin and goes into the black probe of my ammeter. It will flow through the ammeter and come back on the red probe, the electrons, through this pin, and then onto row 12 here, then up through R1, and then to the positive side of the source. So what I'm doing is I'm forcing my meter to be in the current path. Everybody follow? The ammeter puts the itself in the current path. When I go to do so, I should read something close to my 7.69, and the reason why mine is a little low, because my voltage supply is a little less than 5 volts. But take a look at the meter. Are the leads set up correctly? Black is on common, red is on this port, which shows I can measure milliamps on this port, so it's good where it is. Is my dial in the ammeter range, this green range here? And is it in the appropriate scale? Oops, come back here, sorry. Is it on the appropriate scale? I'm hoping to read 7.69, so I want to pick a scale that is just above my value. If I'm trying to read under 10, 7.69 is under 10, so I set this under 20. So 20 milliamps is my maximum. I don't want to go to 200 milli. I don't want to go, 200 milli is a little higher, less resolution, and I don't want to go here. That's 2 milliamps. So up to 20 milliamps is fine. This is the appropriate scale, gives me good resolution, and I'm happy. Okay. Once I get the value, I write down all the digits. I now want to move to circuit point B. In order for me to do this, I disconnect my probes. I have to rebuild the circuit. What do I need to do? What did I just say? I have to rebuild this junction between A and B after I pull out these pins. So that means I have to put the jumper back in here and then pull the jumper out of here in order to create a new open, which is what I'm doing at point C. So here at point C, I've put my jumper back. I've pulled this jumper out, created a new open, connected my black probe with a pin to the top of R3, connected my red probe with a pin to the bottom of R2, and again, trace the path for electricity to flow. Electrons flow from the negative rail, flows through the yellow jumper, this part of the board, through the orange jumper labeled ground, into point D, up through R3. What happens at here? It doesn't jump to the second resistor. It's got to go through this pin, follow the pin to the black probe, into the ammeter, through the ammeter, coming out of the ammeter on the red probe, the electrons, to this pin, to this row, finally to R2. And once we get to R2, it flows up through pin B jumper, through R1, through the jumper at the top, and into the positive side of the source. Did we create an open? Did we put our ammeter into that open and then force the electrons to flow through the ammeter? And when we go to do so, the meter should read, boom, right there, 7.41 in my case. Again, the meter is set in the ammeter mode. The probes are set correctly. The value is measured off of point C, the same way we measured off of point B. Were we able to confirm with this set of images that the current flowing through point B is exactly the same as the current flowing through point C? Does that help substantiate what we need to understand about series circuits? That current is the same in all parts of a series circuit. Yes? Then, okay, we're not satisfied. We want to go for one more point, and we shall. I've removed the ground jumper. But in order to measure current here, what you don't want to forget, you have to rebuild the jumper that was pulled out. So initially we pulled out the jumper at point B, we have to put it back. Then we pulled out the jumper at point C, we have to put it back. You can't create more than one open at a time. We only want one open. So that's now closed. That's now closed back up. We pulled the ground jumper. You don't remember the ground jumper? Here's the ground jumper. The ground jumper was at the bottom of the third resistor going to the negative rail, okay? And so what we've done here is we've yanked that orange jumper and now put the ammeter across the open. So I have the red lead at the bottom of R3, and I have the black probe over here tied to this yellow jumper that goes to my negative rail. So again, let's trace the path for electrons here. The electrons flow into the yellow jumper to this row 24 set of tie points, follows underneath the board to this pin, comes up this pin to this probe. This probe will take me to the ammeter. The ammeter will read the current. And then on the other side of the ammeter, the electrons will come back to the circuit board on the red probe down to this set of tie points, row 24 here as well, flow into R3 through pin C, R2, pin B, R1, over the top, back to the red rail. I have completed my current path. The ammeter is in the current path. And I read pretty close the same. When you're getting into measuring currents, you're going to find that they're not going to be spot on the same as your calculations each and every time. Real world currents and real world measurements on the board can fluctuate slightly to the 100th of a digit for a number of reasons. Most common reason could be I've used these boards many times, maybe some residue in some of these tie points. So as I go to jam a wire in, maybe there's some impurities in there that'll shift this last digit a little bit. So it's not at all uncommon, and you've done nothing wrong if this last digit fluctuates a little bit between point C, point B. So point B was 741, point C was 7.41, and the ground point was a little bit higher, 7.43. There's nothing wrong with having them slightly off because of real circuit conditions on the board. Okay? Okay, so we're going to get to do this live on my board. And somebody has a question for me?
Yeah, I just have a quick one.
Yes.
What happens if you use the wrong scale on the ammeter?
You'll get less resolution. You won't burn up anything, but you'll get less resolution. So you will have less than a full complement of digits to write down, and so you might end up with a decimal point something. So you always want to use as revealing a scale as possible. All right. So I'm going to take us off the share screen. I'm going to demonstrate this to you live. So let's move this guy here, move this guy here, move this out of the way, this out of the way, get my circuit. And let's bring this guy down. That looks pretty good. Focus, focus, good. Bring in my multimeter, that's good. And let's bring in a probe. This guy goes here. And this guy goes here. Turn the circuit on. Circuit is on. And for some of you, and hopefully I helped to clear this up in the Discord chat, some of you, when you were doing your measurements on the most recent circuits, F and G, you were getting some values. They don't match my calculations. They don't match my calculations. Well, many of you may have left the LED on your board. And if you leave the LED on your board, it will mess up your calculations. So for example, if I were to turn off my circuit for a moment, go to pull this particular jumper and jam in my LED, and light it up. Okay, now I've got a lit LED. So when you go to make measurements of the voltages based on your calculations, you can't leave the LED in there because it drops its own amount of voltage, which will skew the amount of voltages you measure here based on your calculations. So what you need to do, and you remember, is to yank out the LED and put back in or replace the LED where it was with a jumper wire, which I'm going to put back in here. All right. And now I've completed the path for electricity to flow, remove the LED, and light this guy up, and I should be able to verify my currents. So following the directions that are on our previous slides, first thing to do, you got to make sure your probes are set properly to common and milliamps, which it is here. Then you have to set your dial to measure current. Now this region of the meter is volts. This region is AC volts as indicated by the squiggly line. This is DC volts indicated by the straight line with the dots underneath. So DC voltage here, AC voltage here, off is here. My ohms are down here, and my current is over here. And so I've predicted 7.7 something change. So I want to go, this would be the 2 milliamp scale. 2000 micro is 2 milliamps, not high enough to measure 7 milliamps. So I go to the next scale above, which is 20 milliamps. So are the probes set correctly on the ports of the multimeter? Is the multimeter set to measure current? Is it the right scale? Yes, yes, and yes. Next, on the schematic, on the circuit, we have to decide where to measure the current. And I've decided we're going to measure this at point B. So I'm going to create an open by yanking out this jumper at point B. Now I have an open. Now, because I have an open, if I'm going to use my little hooks, I can hook this up here, and then I can hook this guy up here. And now I'm showing 7.53 milliamps, pretty close to my 7.69. Is everybody following how our current is set up? So if I follow my electrons, here's my electrons. My electrons are flowing from the blue rail through this yellow wire, through this jumper wire, up through the third resistor to the point C jumper, into the second resistor, up through the second resistor, in through the negative probe, the black probe, into my amp meter, out of my amp meter on my red probe, coming back to the board here, to the first resistor, back to the positive rail. So I have forced my meter to be in the current path. That's how I'm verifying my current for junction point B. All right, so now what I want to do, turn this guy off, disconnect. I want to now make a new open. So if I create my open here, I have to recreate my circuit close there. So I just simply move the jumper from here to here. Have I rebuilt my circuit at point B? Yes. Have I created a new open at point C? Yes. And I'm ready to make that measurement. Again, I will hook this up here on the positive side, hook this guy here up on the negative side, and turn the circuit on. And I end up with 7.53, 7.52 in that range milliamps, which is great. Now, we said we had to be mindful of polarities. Suppose I do this. Suppose I hook up the red here and I hook up the black here. Won't blow up my meter or anything, but if you look carefully, you see the negative sign on the display of my multimeter, 7.51, 7.52 milliamps, but it shows negative. Does it mean I've done anything wrong? The answer is no. It just simply means that the red probe senses the negative side of that open and reflects that current reading here as being negative. So I just simply, if I want to feel better, have it match my numbers, I will put this back the way it was, and no more negative sign. It is a positive 7.52. Are we okay with measuring current here? Done. Then clear this guy up and rebuild my circuit. Turn this guy off, rebuild my circuit, use this jumper, put this back in place, and I'm going to pull this guy out here. I've removed the jumper that bridged my dip groove, and since I don't have anything here to grab a hold of, I'm just going to grab any one of these jumper wires, and what I've done is I've just taken the blue one and I've kind of unbent them, and I'm going to hook this guy up here as a measuring device, and then I happen to have a red one just because I can. Hook it up here, So I'm going to use these 2 pins, connection points. So I'm going to hook up my black on this side, hook up my red on this side. Is my meter still in the current path? If I trace this, are my electrons going to flow from the blue rail through the yellow wire into this blue jumper, into my black probe, coming into the ammeter, going through the ammeter, coming out of the ammeter on the red banana, red leads to the red probe, to this jumper pin connecting to 3, 2, and 1 resistors back to this top? Yes. And now I turn the circuit on, and in doing so, there's my 7.53 milliamps. Does everybody now see in real life how this all worked out for measuring current? So far, so good. Any questions here at this moment? Okay. You had, and I had asked you to retain your circuit G, because in your circuit G, you have a worksheet that is loaded into Canvas, and let's point you in the direction of that right now. And in Canvas we have, let's load this up, and it will be circuit G. It's a Word document. How far down did I put it? Voltage and current analysis right here. Let me just open it up from a thumb drive. Cool. And let's go to share. All right, and let me get rid of some of the things that I don't need. All right. So this is a circuit that you have built, that you have taken selfie pictures with, and that we're going to analyze a little differently now. We're going to analyze this for voltages at very specific points, reference to ground, and then we also have voltages between multiple points. So if we take a look at the table that's on the left, the table that's on the left goes to show our predictions, our calculations, if you will, if the switch was open. Here's the switch open. And the table on the right shows what's happening if the switch is closed. Then you have a different set of predictions for voltages and such. Let's do this together for some of these points. I'm going to grab my circuit G. Here's my circuit G. Pull this guy out, put the power supply in place, connect the power supply cord. Okay, my circuit G, and I'm going to have a slightly different angle on this. So I'll have it come out this way. That'll be good. Nice. All right. So we are asked to predict voltages at very specific points. And what do you think we should have at point A? And if it's a single letter point, remember the red probe goes to the single letter. Where does the black probe go if you're only shown a single letter? Do you remember? It goes to ground. If you're shown VA as a single voltage at a single point, the other probe always goes to ground. So look at the schematic. Ground is at point G. A is up here. If I put my red probe on A, I put my black probe on G. What will my voltmeter, what do you predict the voltmeter should show? What might I put in here?
The value of the voltage source.
What my voltage source, and how much is my voltage source in this case?
5 volts.
I have 5 volts. Now, does it matter that the switch is open?
No.
No. Is there current flowing in the circuit with the switch open?
No.
There is no current flowing. But between point A and point G, I still have 5 volts. And that was one of your homework questions. Your homework question asked, could you have voltage even when there's no current flowing? And the answer to the question is yes. If you look at briefly at my insert in the grid, here's my circuit G, and what am I holding in my hands? Is a 9-volt battery. Does this 9-volt battery have voltage I can measure? Yes. Is there current flowing out of this right now? No. So I can have voltage without current flowing. So on my schematic between point A and G, I can have 5 volts without any current flowing. So I'm going to do that. I'm going to verify. We say it's going to be 5, so I'm going to go ahead and put my black probe on G, and I'm going to go ahead and put my red probe on A, and I'm going to hook up this guy to here, and this guy to here, and I have to turn on my multimeter to read voltage. Okay, I expect to see 5, and let me see if I do actually are able to see 5 volts. So let me get the camera in position and without the glare. Okay, hopefully no glare there. And let me go off the share for just a moment. Now you see this in glorious detail. Light this guy up. Do I have something close to 5? And my board is, maybe I got short shrifted or something, but my board doesn't come all the way up to 5. Some of yours go over 5. So woo, you got a bonus. So mine comes up to 4.95, pretty close to 5. We predicted 5. We'll call it close to 5, but I'm going to write down what the meter shows me, which is 4.94 at this moment. So that's what I write down. Voltage at point A. All right, now here's the thought. Let's go back to the share and see what the next points of interest may be. Let's take a look at point D. So here, right here, V. So we said 5 volts here, so I'm going to type 5 V. Okay, 5 volts. And then we measured 4.94. 4.94 V. Boom. All right. Let's take a look at point D, the voltage at point D. So where is point D in my circuit? Way up here in the upper right-hand corner. And it is the junction where the resistor R3 is going to be connected to the switch, yeah? Well, my red probe will go to point D. My black probe is still at G. How much voltage do you think, if any, will my red probe see if I hook it up at D? Anybody have any thought about that?
5.
Harpreet says 5. Anybody else have an opinion? I don't expect you all to know because we haven't discussed it until now. That was a good guess, Harpreet. So Harpreet says, what's that?
0.
Tony says 0.
Yes.
It might be plausible because we have an open switch here, but I'll show you something very interesting. So we have 5 volts offered by one classmate, and we have 0 volts offered by another classmate, and now we're going to do a measurement. So I'm going to come off of the share, back to here. This guy is still lit. All I have to do is to move my jumper pin. So I'm going to use a jumper pin, and I'm going to insert it at point D. So here is point D. It's inserted at point D. And let me move this a little bit more over this way. There we go. And I'm going to hook up my red probe. I'm going to untangle this from all this mess and hook it up on the top side of the circuit so it's not in our way. And hook it up there. So is my red probe presently at point D, which is the far end of the third resistor? And is my black probe still at ground? And lo and behold, my circuit is on, and it is not 0. It's pretty much the output of my board, which is, you know, close to 5 volts. So how is that? How is it possible with the switch in the open position, and you know on our boards, unless I press this button, the switch is open. How is it possible that I'm going to measure 5 volts there when I have this open? And the reason why it's possible is this. Point A and point D have no difference of potential. Is there any current flowing through your resistors, R1, R2, and R3? Any current whatsoever if the switch is open? No current. If there's no current, then if you go to calculate, there's no ohms here, okay? This is as if this is a single piece of wire, as if there's no resistance. The potential, the push that I have to move electricity at point A is the same at B, same as C, same as D. I will measure 5, and watch this. I'm going to move this point to point C. Here it is at point C. What does my meter show? Almost 5. I'm going to move this over to point B. Here it is at point B. What's it show? Almost the full 5. Okay, move this back to point A. What's it going to show? Point A on my red rail. I'm in the shade here. What's it going to show? Pretty much the full 5. Okay, all right. Let's try another point. So let's go back to the share real quick, and let's go share, and here, and come up with another interesting point. Anna, why don't you pick another interesting point for us? Which prediction would you like to help us make?
Point F.
Point F. Okay, everybody look at point F, voltage at point F. Look at where F is in the schematic. Now, remember, after I prove that the circuit lights up with my LED, and here I yanked it out, but here, let me just do this with you. Here we go. Okay. All right. So after we proved that the circuit lights up with the LED in place, what did I say for a number of you who showed who contacted me and said my voltages are all wrong? I said after the LED lights up to show you have a good build, you pull the LED out, you put in a jumper wire in place of the LED, then you do your voltage measurements. All right, so that's what I'm showing here. I showed that the LED in my schematic has been replaced with a wire. So Anna says, let's go ahead and measure between F and G. What do you think, Anna, would be the voltage between F and G?
5.
Let's see if I'll put down 5V for the voltage at point F. And now let's go see what happens in the actual circuit. So here's the circuit. I press the button, LED lights up, yes? So once that tells me my circuit build is good. I will yank out the LED, set it aside. I will grab a jumper wire. Go ahead and put this guy in where the LED was. And the switch is open. So I'm now going to pull out my red pin, and I'm going to stick this at point F. So point F is right here on this side where the LED was. And I put the black probe still stays at ground. Now I put my red probe here. And we thought it might be F, 5 volts. Let's see what happens. It's 0 volts. And it ought to be 0, and let me explain why. You should be able to see so here. Is the red probe physically connected to my red pin to point F? Is point F connected with a jumper wire to point G, because this replaces your LED? Is point G connected to point G with a jumper here? Is this yellow jumper connected to my blue rail, which is point G? connected to my black probe. Is my red probe and my black probe, are they connected to physically the same point? Yes. This is electrically the same point. And remember, we're not going to be able to measure voltage unless there is a difference of ohms between here. There's no difference. This is one solid wire underneath the board. So since there's no ohms in here, this is one piece of wire that's made, one continuous path made up of many pieces of wire, but still 0 ohms. I'm going to measure 0 volts for this reason. Okay. Okay. All right. That's a good learning lesson. Let's go to the other side and see what happens when we actually do light the circuit up. Let's go to here. Let's try something on the other side. So on the other side, the right-hand side, I have the switch closed. So I can simulate a switch closed without having to, well, I can push the button. I can simulate the switch closed by pushing the button on the board. But what I've done here in the schematic is I put a little jumper wire in place of the switch showing it's closed. Now I have continuity. I have a complete path for electricity to flow. Pick a point of interest where you want to measure. Pick one of these, and maybe some of the more interesting ones near the bottom. Let's see. Dana, would you like to pick something here? Anyone, and then we'll have everybody throw in their thoughts.
Have you done E to F?
E to F. No, we haven't done E to F on this side. Okay, so we're on the right-hand table. We're looking at E to F. So E is here on one side of the switch. F is over here on this side of the switch, but I have this closed. So look at my schematic. E is here, F is here. So if I put the red probe here and the black probe here, what's between E and F? Is there any resistance? No. Are they connected? Yes. What are they connected with? Essentially 3 pieces of wire. Are there any ohms between E and F? No. This is as if this is one long wire. These are E and F electrically the same point. If I connect the red probe at E, black probe at F, there's going to be no potential difference between these 2 points. It's a 0 because it is one wire. Okay. So I'm going to go ahead and do that E to F on the board. So I'm going to go ahead and put, this is to E, that's E, and this one will go to F. This guy's now at F. So here's E to F. And when the switch is closed, it behaves like a wire. So my current path is from the red pin through the switch closed, through this jumper wire, and there's no resistor in the way. It is one wire, one current path made up of several wires. And I'm going to put this up here. And again, the switch is closed, so I'm going to push this button down. What does we expect? 0. What does my meter show? My meter shows 0 volts. What happens if I open the switch? What's my E to F? So E to F, we measured 0V. We thought it might be something else, possibly 5, who knows? And then it instead equals 0V. Okay. So how about, what would we have E to F if the switch were open over here? Here's my E and here's my F. What would we have between E and F if the switch were open? Who would like to guess?
Infinity?
Let me go to the schematic so you can see. Okay, so we're filling in the chart. So for E to F, we're on this cell here with an open circuit. So here is point E, here is point F with an open switch. And so somebody throw me out a number here. Who thinks what?
5 volts.
Somebody says 5 volts. Javier says 5 volts. Who else has another idea?
Also 5 volts.
Oh, another vote for 5 volts. Who has another idea?
I don't have another idea, but I'm going with 5 volts too.
Okay, good. All right, we got people voting for 5 volts. And let's go ahead and see what happens. Should we have 5 volts? The answer is yes, we should. Because if the black probe is at F, it's the same as ground. If we have the red probe at E, again, it is the same as if it were connected all the way up to A. As long as there's no current flow, then this wire here becomes one and the same wire all the way back to the source. We expect to see the full 5. If I go to stop the share, we're now here, and I'm going, oh yeah, we now have an open switch. Well, I just simply don't push the button then. It is now open. There's my 5 volts, or something close to it on my power supply. Okay, okay. So this is what you get to think about. You get to think about, what do you predict the voltages to be when the switch is open? What do you predict the voltages to be when the switch is closed? So you do your calculations first, and then you will do your measurements. Okay, anybody have any questions regarding this exercise? That's why I said for you to retain the circuit and to make sure labels were in place to help you work your way around. Any questions? Okay, so let me close the evening with this, because we're at 9. So let me close the evening with this and say, I've asked a number of you to remind me of something. What did I ask you to remind me of?
Your middle name.
Oh, who said that?
Chisomaga.
Chisomaga. Did that come up in a conversation we had either via text or otherwise? Yes. And who knows? I shared my middle name with people. Who knows what my middle name is?
Flexible.
Flexible. So here's the thing. Second week, we had the typical second bumps in the road, and that is because you're learning scientific notation and engineering notation, engineering prefixes on top of that, and calculating various aspects of Ohm's law. There's been some challenges in being able to meet some of the deadlines. And so my middle name is Flexible. So for the first 3 weeks, first how many weeks? Tres. Uno, dos, tres. For the first 3 weeks, you can have a little flexibility with respect to those deadlines. I have mentioned that to a number of you, and I've also made note in my comments as I've graded the work that has come to me, and I made comments, no late penalty this time, and that there will be no late penalty for all of the third week dates that are due as well. Give you some time to ease into this, get practice, get a rhythm going, and I think a number of you are doing really, really well. So don't worry about your assignments coming in late for the first 3 weeks. Scoring 50% as opposed to up to 100%, that will not happen unless you don't turn something in. If you don't turn something in, then after 3 weeks, it's going to be a 0. But I figure, some degree of flexibility. So this flexibility is good for the first 3 weeks. But this hopefully will help some of you who have developed a little bit of anxiousness about where you stand and can you get the work done. And yes, you can easily get the work done, because truth be told, the math is middle school, early high school stuff. We're really not doing any tricky math whatsoever, but we're learning new ways of using the math, using the calculator with the principles of electronics. And hopefully, because we're doing this with circuit boards, that this helps you understand the principles that we're learning in theory by putting them to a real-world application by building these circuits. So you'll find that the circuits will continue in terms of how interesting that they can be, what you can learn from them, and all of the PowerPoints and things that we've been generating. All this is new. The course has never ever been taught fully online before. It's always been hybrid, and as it's been hybrid, I've always been able to see your smiling faces in the lab on a nightly basis. And so all of these things I would be writing on the board or having discussions verbally. But because we're doing this online, everything that you see in the PowerPoint is completely new and never been generated before. So when we go to the keystroke sequences of this third week's PowerPoint, those keystroke buttons were individually drawn in a separate drawing program and put together, and so you can have the keystroke sequences. So all that is very time consuming to do, and as I discover things that we discuss on Thursday, I've modified the first week's PowerPoint and I've modified the second week's PowerPoint. So you have to look at those PowerPoints. Whatever's current in Canvas is the most recent version. I've updated to version 4 now for I think last week we're up to version 4 because I've modified it and updated it a few more times since you first saw it. So what to do between now and Thursday? I've given you a sample of what the quiz will be on Thursday. The quiz on Thursday will take place after our lecture and catch up. And we will do this in real time. We'll do this together. And we will have a test on Tuesday, and the test on Tuesday will be more of the same. It will not be particularly lengthy. It won't have quite as many, because we have a lesson to learn for next week, and that's more critical, I think, than a lot of time that's needed for taking a test. But what can help you between now and all of that is put your information into your composition book. Go back to PowerPoint of week 1 and glean through the PowerPoint, and what can you put in here? Bohr's model of the atom, the subatomic particles, how are they charged? What are the rings about? What are the energy levels about? What is the valence band about? It takes energy to free the electrons. What forms of energy? We had heat, light, electricity, magnetism. We had a list of them. You should have that written down. You should have the powers of 10 written down from 10 power, from certainly trillion down to trillionth. You should have at minimum those, if not the full chart. You should have the electrical terms. What electrical terms have we discussed so far? Voltage, current, resistance, and power. You should have at least those 4 of our electrical terms for symbols, for units, for definitions, for symbols for units. You should have that written down so it's all here handy for you. You shouldn't have to go looking for this paper or that paper or that paper. You can write down the worked out examples in here too. So this will be your guide to your go reference for anything that you need. So that's what you can do between now and Thursday, or between now and when we next meet. But between now and Thursday, look over the homework assignments. We have Khan Academy that will help support the theory of what we're doing. We have the WSIC videos from the electronic tutorial source. We have those. So 120 points for each of those. That's 240 points right there. Look through those. Some of the topics, a lot of those topics I've already discussed in lecture last week and this evening, so you'll find going through them pretty easy. What you ought to do is when you go through them, write down in your notebook. You have a question, write it down in your notebook. This is a question, put a Post-it in there. I got to ask Code this question next time we meet, or I got to ask him on Discord, and then write down the answers. And then if you all need more practice, then what I'm suggesting, as I've said, get on with Discord with each other and throw some examples back and forth. There's a nice study team that was formed by one of your classmates that there's a lot more intense chatter going on there of ideas and questions. I don't understand this. Can you explain this? And it's nice to see that banter happening between you all, because it develops a culture, not of competitiveness, but a culture of helping each other, supporting each other, and that's the culture that I want to foster for us in this class. Okay? Okay. So I won't take up any more of your time. I'm a little bit after 9. I apologize.